Hello and welcome to Sorcerer's classes. In today's video, we'll be looking at some of the concepts relevant to some topics in electrostatics, which is relevant for the entrance exams, the post-undergrad, postgraduate entrance exams that you actually take, for be it for admission to PhD program or master's program or lectureship, such as the IIT JAM exam, the UGC NET exam. And they all have, in their syllabus, they all have electrostatics as a part of the physics syllabus. So I have done some previous videos on electrostatics, and I discussed electrostatics in vacuum mostly there. I started off with Coulomb's law, and then I discussed the concept of electric field, the concept of potential, and how they are related to one another, and finally I concluded with Gauss's law. This was Gauss's law, and I concluded with it, and I showed both the integral form of Gauss's law and the differential form of Gauss's law. So that was all electrostatics in vacuum. So vacuum is characterized mostly by, here in the case of electrostatics, vacuum is characterized by epsilon 0, which is the permittivity of free space. But now we'll actually go into electrostatics in medium, and in this today our video will be on conductors. Electrostatics in conductors, and by conductors I mostly mean metals, because metals, they tend to have a lot of free electrons, and you'll see how this influences electrostatics for the case of metals. For the case of dielectrics, it's something quite different, so I'll be discussing them separately in two separate videos. Today's video is only going to go to conductors. And so let's say we have a conductor, and let's say I take a very nice looking conductor, like a rectangular piece of slab. It's a metal slab, and it has a lot of free electrons inside it. And let's say now I put it in an electric field, and just for the sake of convenience, I'll assume that the electric field is uniform. It's a uniform electric field, which is a very special kind of electric field, which is uniform in space, because electric field, remember, electric field is not supposed to be, according to Coulomb's law, electric field actually goes down with distance. It's 1 by r squared. So this is a very special kind of electric field, and we often encounter this kind of electric field problems in entrance exam problems, and just to simplify things. And this is a metal slab. This is a metal slab. So what happens when I put a metal slab in an electric field? Does the electric field penetrate the metal slab? Does it go through? Well, not quite. This is how it's going to look like. Electric field is going through the metal slab. Not really, because of the fact that I just said metal slabs have a lot of free electrons, and these free electrons are very light. Electrons are very light, and they're going to respond to the electric field very quickly. And when I say very quickly, it's the time taken for the response time is about, it depends on a few things. It depends on the conductivity, of course, and sigma t. It depends on sigma, and it can also depend on the epsilon value, the metal permittivity. Let's not go into that, but the response is very fast. And what happens is, the moment you put it in an electric field, the negative charges, they respond to it. And since electric field, remember, electric field is directed from positive charge to negative charge, so there must be positive charges here. and there must be somewhere negative charges here. So in the electrons are negatively charged, they're attracted to positive charges, so they travel opposite to the electric field. They go on this side, and on the other hand, the positive charges are left on this side. And what they do is this charge separation. There's a charge separation that happens. It sets up its own electric field. This is another electric field that is set up, and let's call this electric field, let's call the outside electric field to be E applied, this electric field to be E induced. And what happens is this movement of electron continues until E induced equals E applied. So what happens is that the induced electric field completely cancels out the applied electric field, and so there is no electric field inside a metal, no E field inside a metal. No E field inside a metal. You essentially, a metallic surface will shield out all electric fields that are outside it. Will shield out all the electric fields outside it. There's no electric field inside a metal, and what happens is that this induced electric field cancels out the applied electric field, and all you end up having is charges just lying on the surface. So the electric field, so the electrons are distributed on one side of the metal, the positive charges are distributed on the other side of the metal, and this need not be a very nice looking slab, it can be any slab, and the charges will be induced on the surface here as well. Now there are some consequences. Now of course, what you can do is you can ground this metal, you can ground this side. And what happens is electrons flow in from the earth and basically neutralize the charges here. So in the end, what happens is you're left with just negative charges distributed on the surface. And now there's another consequences to it. What about the electric field lines? What about the electric field lines of a metal surface which is charged? So if you have a charged metallic surface, the electric field lines, you can argue it out, the electric field lines have to be perpendicular, to the surface at every point. And E is normal. And how do you know this? How can we say that E is normal? And it's very simple argument. As an argument, it's very simple. Because if the electric field line was not along the surface, the area vector, then what would happen is that there would be an electric field line that is normal, and there would be a tangential component of the electric field line as well. But what happens is the tangential component will move charges around. And so the charges can't be static if there's a tangential component. Charges cannot be static with ET equal to ET non-zero. Charges cannot be static with ET non-zero, which means for static charge distribution, for static surface charge distribution, ET has to be zero, and E has to be equal to En times the normal vector. En is always normal, So E is always normal to the surface of the metal. Now we can argue, which means that electric field is always normally directed to the surface at every point. Wherever you have the surface area vector pointing, the E has to point along that direction. It's always normal to the surface. And you see that this property is very useful. Now, we have said that there is no E field inside. So what about if you don't have E field inside? What about the distribution of the charges on the surface? Is the distribution uniform? Is the distribution uniform? The answer is no. It is not uniform. Because the distribution charge density will depend on, is proportional to the curvature, or basically surface area. Charge density is proportional to surface area. Let's say we have a surface, a metallic surface, say where we have charge distributions everywhere on the surface. You can automatically see that some points, some parts, especially this part, is very pointed. It's pointy looking, and therefore there is a lot of charge distributions here. And this basically follows from the definition of charge density. If you look at the surface charge density expression, which is sigma. Sigma is delta Q over delta of S. That is sigma, basically. Sigma is delta Q over delta of S. Now if you see for the same charge distribution, if you reduce delta S, sigma S has to go up. But delta S going down, sigma has to go up. So and delta S goes down when you have a small surface area. When you have a small surface area and delta is small, then sigma will be much higher. And therefore, you have a much more higher distribution of charge in this region than anywhere else. So now we have already shown that the electric field is normal to a metallic surface, charged metallic surface, and the charge distribution is completely confined to the surface. What about the charge distribution? How can we draw any conclusion about what the electric field should look like? And the answer is yes. We have to again use our good old Gauss's law. We can use a good old Gauss's law, and what we do is we can draw a Gaussian surface. We can draw a Gaussian surface. Let's draw a cylinder. Why? What allows us to draw a Gaussian surface? So in the previous video lecture, we said something about the nature of the Gaussian surface. The Gaussian surface depends on the symmetry at hand. If you know the symmetry of the problem, if it's radial symmetric or it's spherical symmetric problem, you can very easily draw the Gaussian surface. If it's a spherical symmetric problem, the Gaussian surface is a sphere. If it's a radial symmetric problem, then the Gaussian surface is a cylinder. In this case, we see that electric field lines are actually normal to the surface everywhere. It's normal to the surface everywhere. And that would allow us to draw a cylinder as a Gaussian surface. Let's expand this view up a little. Let's say this is the surface, and this is our Gaussian surface, with one half of the Gaussian surface inside, and the other half outside. This is our Gaussian surface. Now we see something. We see that since E is 0 inside, so there is no flux from here. Phi 0. See, the Gaussian surface, the closed surface integral, is E dot ds. It's E dot ds. and you see that there is no E dot ds. E dot ds is basically flux. There is no flux from here, and there is also no flux from the curved side. And why is that? Because the curved side surface area is, the area vector is an S, but the electric field is directed normal. It's directed along the normal, and that's why E n cap dot ds s cap for the curved surface will go to 0 as well. It goes to 0. And therefore, the only surface which has a flux out of it is the surface outside, the circular surface outside. This surface has some flux. And so for this surface, En ds equals 1 over epsilon naught, and now we can assume a sigma as a surface charge density. And we can write this charge as sigma dot ds. You see that En will come out to be sigma over epsilon naught, or if you want to write it as a vector form, it will be sigma over epsilon naught n cap. You see the electric field is also dependent on surface charge density, so wherever you have sigma higher, so if you have sigma higher at some point, electric field will also be higher something at that point. The sigma electric field depends on the sigma. It is dependent on sigma, and this is exactly what happens for metals. Electric field points normally. So let us again go through what we have learned. For metals, first of all, the charge distribution has to lie on the surface completely. There cannot be any charges inside, and so by consequence there is no electric field inside, and this electric field on the surface has to be normally directed at every point. There cannot be any tangential component of electric field because that makes the charges move around. But the distribution is not uniform. Distribution depends on the curvature, the surface curvature, surface area, because sigma itself is dependent on area. So wherever you have higher curvature or smaller surface area, the sigma to be higher. And now we have shown, now basically we have shown that En is sigma over epsilon, En is sigma over epsilon, or E equals to sigma over epsilon n cap. So E depends on sigma as well. Where we have higher sigma, we also are going to have higher E. And we came to this conclusion simply using the symmetry of the electric field and by using Gauss's theorem. So that concludes it for today's video. In the next video we'll learn more about conductors and eventually we'll go with dielectrics. I hope you found this video useful. Thank you for watching.